Good morning and welcome to our class. Today we want to continue our discussion on time series model. Yesterday during our classes on time series models, we looked at in details on moving average models of order one. And today we want to continue in that trajectory by looking at moving average models of order two, abbreviated as MA of order 2. And the discussion on this model in time series is going to center on the following. We are going to look at how to write the model of MA of order 2. Model of MA of order 2. We are going to look at the model. We are equally going to look at how to obtain the mean or the expected value of the model of MA of order 2. So we look at what the mean or what we call the expected value. The expected value of MA of order 2. We are equally going to look at what we call the variance of MA of order 2. Look about the variance of MA of order 2. Then we are equally going to look at what we call the autocovariance. The autocovariance. We are as well going to look at what we call the autocorrelation. The autocorrelation function of MA of order 2. Then we now look at what we call the invertibility condition. Invertibility condition. Invertibility condition of MA of order 2. So our discussions this morning are going to center on the following items. So we are first of all going to begin by writing the model of a moving average model of order 2. We are going to write the model in two ways. One contains a constant and the other one, the constant is assumed to be 0 and then it is removed from the model. The first model is written like this. Do remember that yesterday when we talked about MA of order 1, we wrote the model of MA of order 1 as we had y of what of t is given as we had theta 1 a of t minus 1 plus what a of what of t. And we gave a condition. The condition is that this a of t follows a normal distribution with mean 0 and constant variance sigma squared of what of a. Is one of the models that we wrote yesterday for MA of order 1, where the mean constant in the model has been assumed to be 0. We equally had another model for that MA of order 1 yesterday, talking about y of t is given as, we had what? Mu plus, we had what? Theta 1 a of t minus 1 plus what? A of what of t, such that this condition is equally applied. The only difference between the first model and the second model is that the first model didn't contain this mean constant. The assumption here in the first model is that the mean constant is what is 0. But in the second one, we included the mean constant, which might not necessarily be 0 in this second model. It was what we said yesterday about the model of MA of order 1. Therefore, the MA of order 1 is a linear combination of the previous error term of what of the series and then the error term in the current time. We are now going to talk about how to write a model for MA of order 2, which of course is going to be an extension of the model for MA of order 1. If you want to write a model for MA of order 2, it will be written like this. The model will be written like this. Model, it will be written that y of t is given as theta 1 a of t minus 1 plus theta what 2 a of t minus 2 plus what a of what t, such that these are a of t equally follows a normal distribution with mean 0 and variance sigma squared of what of a. If you look at this model and this model, everything that is contained in MA of order 1 is contained in MA of order 2. Just that there is an extension to the second error term of what of the series. So it is a linear combination of two error terms of the series and then the error term in the current what time. That is MA of order 2. So you can equally write the MA of order 2 this way. You can equally have y of what of t is given as, we have what, mu plus theta 1 a of what of t minus 1 plus theta 2 a of t minus 2 plus what a of t, such that this condition applies. So this is how to write the moving average model of order 2. Linear combination of two previous error terms at times t minus 1, t minus 2, and then the error term in the current time. Of course, we should know that this error term in time series language is called the white noise. So when you call it white noise, it is correct. When you call it the error term, it is correct. When you call it the residual, it is equally correct. So this is how to write a model of MA of order 2. So we are done showing how to write a model of a moving average model of order 2. So we are going to go to the mean, or what we call the expected value. Okay? So you are going to permit me to clean here, and then we talk about what the mean. And when we want to talk about the mean, of course, we are going to look at the mean from the two models. So you permit me to clean this. Okay, the second model we wrote for, so we're not talking about the mean, we're not talking about the mean. Talking about the mean, we are talking about the mean, or what we call the expected value. What we call the expected value, expected value. And of course, the second model that we wrote is that we had y of what of t is given as, we had what? We had our mu, or let me start with the first model. So we had what? Theta 1 a of t minus 1 plus theta what 2 a of t minus 2 plus a of t, such that a of t follows normal distribution with mean 0 and variance sigma squared of what of a. For us to obtain the mean of the model, we are to take the expected value of the both side of what of the model. So it becomes that e of y of t is given as e of theta 1 a of t minus 1 plus theta what 2 a of t minus 2 plus a of what of t. So by a way of opening this bracket, we are going to have this. That this becomes what? We have theta 1 e of what a of t minus 1 plus theta what 2 e of a minus what 2 plus what e of what of a of what of t. In this case, I've brought out the constant theta 1 and theta 2 outside the expectation sign, because we know that when you are taking expected value of a constant and a variable, you can equally bring out the constant outside and take the expectation of what of the variable alone, bearing in mind that expected value of a constant is a constant. So that is what exactly I have done here. because this is the expected value of theta 1 A of t minus 1. But knowing fully well that theta 1 is a constant, I have brought it outside this expected expected value sign, and then taking expectation of A of t minus 1. The same thing applies here. This one is A of t. Then we are going to now look at this thing critically by remembering the condition that they gave us, that this error term A of t follows normal with mean 0 and variance sigma squared of what of A. And bearing in mind that we are discussing a model that is assumed to be a stationary model in time series. And a stationary model in time series is one that its mean, its variance, and its autocovariance are constant over time. By implication, the mean of such model at time t minus 1 is the same thing as the mean of the model at t minus what 2, the same thing as model as y of what of t. It remains what constant. So by implication, it implies that the expected value of this error term at t minus 1 is the same thing as the expected value of this error term at t minus what 2, and it is the same thing at t. And you know quite alright that then the expected value, which is the mean, has been given to be 0 here. So this quantity becomes 0, this becomes 0, and this becomes 0. And what we have becomes what? Theta 1 multiplied by 0 plus theta what 2 multiplied by 0 plus 0, which is this one. And by this, everything reduces to be what? To be 0. So this first model, where we do not have the mean constant mu, its expected value is what is 0. And I did say it earlier that in that first model, the mean of the model is assumed to be what? To be 0, and therefore is skipped from the what? From the model. However, when you are talking about the second model that says what? Y of t is given as what? Mu plus theta 1 A of t minus 1 plus theta what 2 A of t minus 2 plus what? A of t. Such that this A of t still follows normal distribution with mean 0 and constant variance sigma squared of what? Of A. And you are told to obtain the mean of this model. You are going to take the expected value of both sides of what? Of the model, and you are going to have something like this. E of y of t is given as E of mu plus theta 1 A of t minus 1 plus theta 2 A of t minus 2 plus A of t, you close. Then you open the bracket. Opening the bracket is going to be, you have E of what? Of mu plus theta 1 E of A of t minus 1 plus theta 2 E of A of t minus what? 2 plus E of A of t. Now, this mu here is a constant, and expected value of a constant is a constant, so this becomes what? Mu plus. We earlier had shown or had explained that this expected value of A of t minus 1 is 0. The explanation is still here. So here becomes what? Theta 1 multiplied by 0 plus here equally theta 2 multiplied by 0 plus what? 0 here. It will make from the whole of here to here to become what? 0. So we are left with mu alone, and we say therefore that E of y of t is given as what? As mu. So in the first model of MA of order 2 written this way, the expected value, which is the mean of the model, is 0. Then in the second model of MA of order 2, which is written this way, the expected value or the mean of that model is given as what? As a mu. So that is how to obtain the mean or the expected value of the model of moving average model of order 2. So we are done looking at the model, we are done looking at what are the mean, we want to look at at the variance. However, before we look at the variance, it is important that we mention that whenever we are given a question like this, we have that y of t is given as something like 2.1 plus. We have what we call 0.2 a of t minus 1, a of t minus 1 plus 0.6, we have what a of t minus 2 plus a of t. And we are told to find the mean of this model. What we are going to do first of all is to identify the kind of model it is. We identify it by looking at, is the time series value at time t a linear combination of what? We now say it is a linear combination of what? Of error terms. How many error terms are we talking about here? 1, 2. At time t minus 1 and at time t minus 2. And then the error term at the current time. Now, if you look at this now, and then you match it with what? With the model of MA of order 2, you find out that you equally have two error terms at t minus 1 and at t minus 2, and then the error term at the current time. So, meaning that this model is a model for moving average model of order 2. So, you now begin to compare the terms one by one. You have A of t here, you have A of t here. You have a term with a of t minus 2, you have a term with a of t minus 2. With that, you'll be convinced that this your theta 2 is 0.6. The same thing applies here, and you'll be convinced that your theta 1 here is your 0.2. And that will now make you to believe that this your mu is your 2.1. And then the expected value is mu, which equally now becomes this 2.1. So that is how to go about the mean of the process. So you permit me to clean this while we talk about the variance. So we want to talk about the variance of the model. So here I'm talking about variance. I'm talking about variance. And of course, for us to get the variance of the model, we have to multiply or to take the variance of the both sides of the model. So you permit me to be using V as variance to manage the size of this board. So I now have what we call V of y of t is given as V into what? Theta 1 a of t minus 1 plus theta 2 a of t minus 2 plus what? A of t. You close the brackets. And I would like to remind us what I said yesterday about taking the variance of the sum of random variables. Yesterday, during our classes on MA of order 1, I did say that when you talk about variance, V of x plus what? Y, that it will be given as V of x plus V of y plus 2 covariance of x, y. This is the rule. And I'm going to apply the principle of this rule while expanding the variance here. So for me to do that, what I'm going to have here becomes, therefore, my V of y of t here is going to be, I have what? V of theta 1 a of t minus 1 plus V of theta 2 a of t minus 2 plus I have V of a of t. I still have plus. I enter the covariance of the pair of the terms in the model. That is to say, I am going to look at the two covariance of this quantity theta 1 a of t minus 1 and then theta 2 a of t minus 2. Okay, so that is to say I'm going to look at this two covariance, or before I write that covariance, we know that here is theta 1 and here is theta 2. So I can bring them outside. I have theta 1, theta 2, covariance of, I now have a of t minus 1, comma, a of t minus what? 2. I am done taking the pair of this and this. I will take the pair of this and this. So I will say plus. I have 2. The only thing involved here is what? Theta 1. Then I have covariance of a of t minus 1, and then this one, a of what? T plus. I will take the pair of this and this, which of course becomes what? 2. Theta what? 2. Covariance of a of t minus what? 2, and a of what? Of t. So that is how to expand these terms here when we are taking the variance of the model. And we are going to remind ourselves something, that these error terms at different points in time are uncorrelated. They are independent of each other. So their covariances must be 0. Error term at t minus 1 and error term at t minus 2, they are independent, uncorrelated. So taking their covariance will now be 0. The same thing applies here. This is t minus 2. So the covariance here is going to be 0. The same thing here, t minus 1 and then t, the covariance is equally going to give us 0. So for that reason, these three terms, this, and this, become 0. And we only have it to be this way, that our var of what? Y of t is given as, we come here. When you bring a constant outside a variance sign, you are going to square the constant. And you have theta 1 all squared v of a of t minus 1 plus, bringing this one outside, theta 2 all squared v of a of t minus what? 2 plus what? V of what? A of t. And of course, we have been told that the error term a of t follows normal with mean 0 and constant variance sigma squared over what? Over sigma squared of what? Of a. And we are told that this model is a stationary model where the variance is constant at all times, implying that at t minus 1, the variance is sigma squared of a. At t minus 2, the variance is t sigma squared of a. Even at time t, the variance of the error term still remains sigma squared of a. And that thing will now imply that if I am calling this place sigma squared of what? Y. Y here is y of the series, is given as, we have theta 1 squared, here becomes sigma squared of what? Of a, which is given here, plus, here becomes what? Theta what? 2 squared, sigma squared of what? Of a, plus we have sigma squared of a for this one. Sigma squared of a is contained this place, and this place, so we can factor out. And this thing will now be able to give us that sigma squared of what? Of a into what is left here becomes what? 1 plus. What should be here? Or let me write this way first. We have theta 1 all squared plus theta 2 all squared plus 1. You close the brackets. It can equally be written this way, that is equals sigma squared of what? Of a into 1 plus theta 1 all squared plus theta 2 all squared. So this is the variance of MA of order 2 models. Moving average model of order 2 models. So somebody can give us equation like the one I gave earlier, or a model like the one I gave earlier, that y of what? Of t is given as either 0.25 plus, we have 0.23 a of t minus 1 plus either 0.64 a of t minus what? 2 plus a of t. And the person says that a of t follows normal with mean 0 and variance either 1.0 0.03. And the person asks us now to find the variance of this model. We now first of all identify the kind of model we have, which of course is the model for MA of order 2. And we know that the formula for the variance of MA of order 2 is given as this. Where this 1.03 is the variance of the error term, and look at the variance of the error term outside. So here becomes 1.03 into 1 plus. Theta 1, of course, is what? 0.23. Theta 2, of course, is 0.64. So we now square them this way and evaluate the final answer. So that is how to obtain the variance of MA of order 2. So permit me now to clean here while we now go to autocovariance of MA of order 2. Permit me to clean here. To obtain the autocovariance of any time series model, the rule is that we multiply the model with y of t minus k. Okay, that is the value of the series at lag k. You use it to multiply both sides of what? Of the model, and then you take the expectation. And whatever thing you are getting there is what we are calling the autocovariance. So I'm first of all going to write the model for MA of order 2, and then I will now use y of t minus k to multiply the model, both sides of the model, before taking expectation. So that is now going to be, our model is y of t is given as, we have theta 1 a of t minus 1 plus theta what? 2 a of t minus 2 plus a of t, such that a of t follows normal, mean 0, sigma squared of a as the constant variance. So I'm going to multiply this model with y of t minus k. So here becomes what? Y of t for this one multiplied by what? Y of t minus k is given as, I'll write the whole of this model, which becomes what? Theta 1 a of t minus 1 plus theta what? 2 a of t minus what? 2 plus what? A of what? T, close it, then y of t minus k. Because you multiply it here, you must equally multiply it this way. Now, when we now write the value for y of t minus k and begin to expand this, it's going to become bulky. So what we are going to do first of all is that we are going to say when k is equals to this, when k is equals to that, to make us now be handling it. So I'm now going to say when k is equals to what? 0. So when k equals to 0, when k equals to 0. So if you say when k equals 0, it implies anywhere you see k, you are now going to substitute with 0. And that thing will now make you to have that y of t multiplied by, here becomes y of t. T minus 0 is just t. So that one is taken care of. This is equals. Here becomes what? Theta 1 a of t minus 1 plus theta what? 2 a of t minus what? 2 plus what? A of t, close it. Then you have what? Y of what? T. Because t minus 0 will now give you what? T. And you know that this y of t is what is defined here. So multiplying this thing with y of t implies multiplying this quantity with the value of what? Of the model here. So what I'm going to do now, I will now say therefore, that y of what? T multiplied by y of what? T is given as, I have theta 1 a of t minus 1 plus theta what? 2 a of t minus 2 plus a of t. Close it, open again. Write the same thing again, which is theta 1 a of t minus 1 plus theta what? 2 a of t minus what? 2 plus a of what? T. I will close it. Now, when we are opening this bracket, we should bear in mind anywhere we see that the error terms have different time values, we are going to skip it because we know that when we take expectation of the error terms at different what lags, that it is going to give us what zero because they are all correlated, and its covariance at that particular time is what is zero. So when we want to now open the bracket, we should be careful, and what we are going to have now becomes this equals, here is t minus 1 and here is t minus 1. So it implies that here the error term is at the same point in time t minus 1. So we are going to have what we call theta 1 all squared, then a of t minus 1 multiplied by a of t minus 1. We are done with this. Using this to multiply this, here is t minus 1 and here is t minus 2. So when you are done multiplying it and you take expectation, it is going to give you what? Zero. Because the error terms are t minus 1 and t minus 2 are independent. They are uncorrelated. So we leave that one. We now take it from this to this. This is t minus 1 and this is a t. They are still going to result to zero, uncorrelated. So you now say plus. You are now here. You are using this to multiply this. Unfortunately, this is t minus 1 and this is t minus what? This is t minus 2 and this is t minus 1. So they are uncorrelated. We leave this. But when we come to this and this is t minus 2, this is t minus 2. So we take it. So this is theta 2 all squared, a of t minus 2 multiplied by a of t minus what? 2 plus. We come to this. When you take this to this is t minus 1 uncorrelated. This is t minus 2 uncorrelated. This is t. So we now have what we call a of t multiplied by a of what? Of t. Okay? So of course now it is now going to be, remember that when you multiply both sides of a model with y of t minus what? K, and you take expectation, you are talking about autocovariance at lag k. But here we have said let k be what? Zero. So we are talking about autocovariance at lag 0. So here becomes what we call gamma what? 0, because autocovariance is represented with gamma 0. We have that therefore we have that e of y of t multiplied by y of t is given as, we have what we call theta 1 all squared e of what? A of what? Of t minus 1 all squared plus, or let me not be using squared, multiplied by a of t minus 1 plus, here becomes what? Theta 2 all squared. We have what we call e of a of t minus 2 multiplied by a of t minus 2. Then plus e of a of t multiplied by a of t. So this is going to be that my gamma 0 is equals. Here becomes what? Theta 1 all squared. Expected value of the error term at t minus 1 multiplied by expected error of at t minus 1 is of course the variance of the error term, which is sigma squared of what? Of a plus. Here becomes my theta 2 all squared. Expected value of error term at t minus 2 multiplying error at t minus 2 is the variance of the error term, sigma squared of what? Of a plus. Expected value of error term at t and error at t is the variance of what? Of the error term. And if you remember, this is exactly what we had when we were talking about the variance, because the autocovariance function of any model at lag 0 is the same thing as its variance, which of course becomes what we call that this is a sigma squared of what? Of a into 1 plus, we have theta 1 all squared plus theta 2 all squared. This is what we have. So the autocovariance function of MA of order 2 at lag 0 is given like this. So I'll put it here. That my gamma 0 is given as a sigma squared of A into 1 plus theta 1 all squared plus theta 2 all squared. This is what we obtained. So we are going to come back here and say when k becomes what? 1, what are we going to see? So you permit me to clean this quickly. And we say when k is now 1, what are we going to have? So when k becomes what? 1, what we are going to do is anywhere we see k, we are going to put 1 there. And this is now going to be y of t multiplied by y of t minus 1 equals, open a bracket, you have theta 1 a of t minus 1 plus theta what 2 a of t minus 2 plus a of t into y of t minus what? 1. The next thing we are going to look at is how can we write the model of a time series at t minus 1. We are going to look at what we have here, and use the idea to write it. So you permit me to clean this top here so that we can write it there. We are still at our autocovariance. So I now have what we call y of t minus 1. I want to write what it is. This is equals. When you had a t here, what you had here was t minus 1. So by implication, you subtracted 1 from whatever thing you had here. But what we are having here now is t minus 1 ordinary. So I will say theta 1 a of t. If you subtract 1 from this minus 1, you have minus what? 2 plus. What you had here was t minus 2, meaning that you subtracted 2 from this t. So you have now theta what? 2 a of t. If you subtract 1 from this 2 from this minus 1, you are going to have minus what? 3 plus. What you have here is exactly what you have here. So I am going to have exactly what I have here equally. A of t minus 1. So it means that for me to multiply this model with y of t minus 1, it is the same thing as multiplying this model with this model here. So I will now say therefore, my y of t multiplied by y of t minus 1 is given by, here becomes theta 1 a of t minus 1 plus theta what? 2 a of t minus 2 plus a of t, close it, open again, write the whole of this thing, which is what? Theta 1 a of t minus 2 plus, we have theta what? 2 a of t minus what? 3 plus a of t minus 1, you close it. When you want to open the bracket as well, be concerned with places where the error terms have the same time lag. Wherever place they have different time lag, of course, taking its expectation will give us what? 0, because they are uncorrelated. So what we are going to do now is to come. When we take this one here, look at the one here, this one goes here. The error term here is at time t minus 1. It is at time t minus 2. So we are going to skip this place. Then we now take this one to here. It is at t minus 1 and t minus 3. So it doesn't work. Then we now take it to here. This is where it works. Where we have t minus 1 and t minus what? 1. So it becomes that this equals, we have what? Theta 1 a of t minus 1 multiplied by a of t minus 1. That is this going to this. Then you come to the second one. The second one will go here. We are lucky. This is t minus 2, this is t minus 2. So we now multiply them plus. We have theta 1, theta 2 A of t minus 2 multiplied by what? A of t minus what? 2 plus. This will go into this. It won't work because the error terms is at different timelines. This will go into this, the same thing. So we now come and carry this last one. When this one goes here, it will not work. When it goes here, it will not work. And when it goes here, it will not work. So we are done here. We now take the expected value of this. So we now say, therefore, that E of y of t multiplied by y of t minus 1 is given as theta 1 E of a of t minus 1 multiplied by a of t minus 1 plus. We have theta 1, theta 2, e of what? A of t minus what? 2 multiplied by a of t minus what? 2. We close. And you should know that when you are saying let k be equals to 1, you are talking about autocovariance at lag 1, written as gamma 1. So what you have here becomes what? Gamma 1 equals, here is your theta what? 1. Here, of course, is the variance of the error term, sigma squared of what? Of A plus. Here you have what? Theta 1, theta what? 2. Here is the variance of error term, sigma squared of what? Of A. So you can take the, here my sigma squared of A is here, sigma squared of A here. So this thing becomes sigma squared of what? Of A into what? Theta 1 plus theta 1, theta what? 2. You close what? The brackets. So, and that thing becomes what we call the autocovariance function of MA of order 2 at lag 1. So I will now write what we have gotten here, that gamma 1 is given as sigma squared of what? Of A into what? Theta 1 plus theta 1, theta what? 2. You close the what? The brackets. So we are going to say when k is equals to 2, let us know what we are going to have. When k is equals to 2. So permit me to clean here. When k is equals to 2 means anywhere you see k, you are going to put 2 there. So what you are going to do now becomes what? That this thing becomes y of t multiplied by y of t minus 2. Because k has become 2, open a bracket, this is theta 1, a of t minus 1 plus theta what? 2, a of t minus what? 2 plus we have what? A of what? T. Then you now say y of what? Of t minus what? 2. So you need to know how to express this y of t minus 2. Just like I did when I had y of a t minus 1. So here is going to be y of what? T minus 2 is going to be. Here you had t here, you subtracted 1. So you are having t minus 2 and you are still subtracting 1. So here is going to be theta 1 a of t minus 3 plus. You are still subtracting 1. So you have theta what? 2 a of t minus what? 4. Reason here is for minus 2. But we are now having minus 2 here. It's going to be minus 4. So you now say plus a of t of what you have here minus what? 2. That's exactly what you are going to have there. So it means that multiplying this model by this y of t minus 2 implies multiplying it with this. So what I'm going to do now is to carry this and multiply this. And that will now be, therefore, y of t multiplied by y of t minus 2 is given as theta 1 a of t minus 1 plus theta 2 a of t minus 2 plus a of t. Close it, you open. In place of this, you put all these things, which is theta 1 a of t minus what? 3 plus theta what? 2 a of t minus 4 plus a of t minus what? 2. You close it. So in opening the bracket, we should equally be concerned with places or the terms where the error term terms share the same time lag. Okay? So if you take this one here, it doesn't go here, it doesn't go here, it doesn't go here, there will be 0. If you take this one here, it doesn't go, it will only go here. So I will now say therefore, my E of y of t multiplied by y of t minus 2 is going to be given as, when it goes to here, to this place, it is going to be this to this is 0 when you take its expectation, this to this is 0 when you take its expectation, this to this is 0 when you take its expectation. We are here. This to this is 0 when you take the expectation. Then it is this to this, which of course is 0 when you take the expectation. But this to this share the same time lag. So it is going to be theta 2 e of a of t minus 2 multiplied by a of t minus 2. You close it, plus. When this goes to this, 0 when you take expectation, 0 when you take expectation, and 0 when you take expectation. So you stop here. And when you say k is equals to 2, you are talking about autocovariance at lag 2. So you are going to say gamma 2 is given as, you have theta what 2 sigma squared of what a, because this is a variance of the error term. Then you include it here, that gamma what 2 is equals sigma squared of a theta 2, which is exactly what we had here. So let us say when k is equals to 3 to quickly see what is going to happen there. So when k is equals to 3, so permit me to clean this place and clean this place. So when we are talking about k being 3, here is now going to be 3, here is now going to be 3. And writing it with this idea now, we are going to have that y of t minus 3 is given as theta 1 a of t minus what? 4 plus theta what 2, we have what? A of t minus what? 5 plus what? A of t minus what? 3. This is exactly what this is going to be. And multiplying this implies multiplying with this quantity. So we have therefore that y of t multiplied by y of t minus 3 is going to be theta 1 a of t minus 1 plus theta 2 a of t minus what? 2 plus a of t. You write the whole of this one, which is theta 1 a of t minus what? 4 plus theta 2 a of t minus what? 5 plus a of t minus what? 3. Then on trying to multiply out, you find out that there is no two terms here that the error terms share the same time lag. Here is 1. Bringing it over here, there is nothing like 1 here. Here is 2. Bringing it over here, there is nothing like 2. Here is this, bringing it over here. It means that when I take expected value of this thing, that e of y of t multiplied by y of t minus what? 3 is going to give me what? 0. And the question is, what do we call this when k is equals to 3? It is called autocovariance at lag 3. So we have that gamma what? 3 is equals to what? 0. So we include it here, that gamma what? 3 is equals to 0. And of course, when you now increase that k is equals to 4, the value of these error terms now continue to shift far away from their values here, from their time lags here, making it stay to be what? To be 0. So it implies that the autocovariance of MA of order 2 cuts off after lag 2. After lag 2, it will cut off. So when k becomes greater than the order of the model 2, the autocovariance becomes what? 0. So what we can equally say here is that for gamma k is equals to 0 for k greater than what? 2. So when k goes beyond 2 now, the autocovariance becomes what? 0. So it means that when someone gives us a model and want us to find gamma 0, want us to find gamma 1, want us to find gamma 2, want us to find gamma 3 down the line, we are going to use these formulas for our evaluation. We use this formula for what? For evaluation. So the next thing we are going to consider quickly is the autocovariance. So we talk about the autocovariance quickly. Sorry, the autocorrelation. Talk about the autocorrelation. When we talk about the autocorrelation, the formula of autocorrelation is that rho k is equals to gamma what? K all over gamma 0. And then we have that our gamma 0 is here. We have that our gamma 1 is here. So if I'm looking for rho 1, I'm going to say it is gamma 1 all over what? Gamma 0. What is my gamma 1 is written here as this is equals to sigma squared of A into what? Theta 1 plus theta 1 theta what? 2 all over sigma squared of A into 1 plus theta 1 squared plus theta 2 squared, which is this. So that this can cancel this and this becomes your rho 1. For you to find rho 2, you are going to say that rho 2 becomes what is called gamma 2 all over gamma what? 0. This is equal to. My gamma 2 is sigma squared of A of theta what? 2 all over sigma squared of A into 1 plus theta 1 all squared plus theta 2 all squared. So you cancel this and cancel this, and this becomes your rho 2. If you talk about rho 3 is equals to gamma 3 all over gamma 0. And you know that your gamma 3 is 0 all over this your sigma squared of A into 1 plus theta 1 all squared plus theta 2 all squared, which of course becomes 0. So that is how to talk about the autocorrelation. Then the last but not the least is what we call the invertibility condition. When do we say that a moving average model of order 2 is invertible? It has a three condition. The first condition is that absolute value of theta what 2 must be less than 1, which of course implies that minus 1 is less than theta what 2, which is less than 1. The second condition says that my theta 1 plus theta what 2 must be less than what 1. And then the third condition says that theta what 2 minus theta 1 must be less than what 1. So when you are given a model and you are asked to check whether the model is stationary or sorry invertible, you are going to check out for these conditions. Once these conditions are satisfied, you quickly say that the model is what is invertible. Yesterday, while we were discussing, we talked about the invertibility of MA of order 1. Of course, MA of order 1 is said to be invertible if absolute value of what theta 1 is less than what 1, which implies that minus 1 is less than theta 1, which is less than 1. That is only the condition for invertibility of MA of order 1. So when we are asked questions to find rho 1, rho 2, rho 3, this is the formula we are going to use to evaluate them from the model of the time series. Thank you very much once more. We really believe that you did not have a challenge or challenges on the course of discussion. But situation whereby you did, please do well to drop your concern or to raise your question in the comment section. And always remember to subscribe, like, and share our videos as we are committed to transforming your understanding about mathematics and statistics. Thanks once more for your audience and stay connected for our next classes.